It's spooky season, so I feel rather silly. Do you remember last episode when I asked if I have a vector and I'm moving through it and I delete something, will it be like, hey, you're modifying this thing I'm iterating over as I'm iterating over it? Stop, you're in unforeseen territory. Turns out that's what this chapter's about.
You just have to say that you're fine when you're not really fine, but you just can't get into it.
So I'm going to start off by saying chapter 4 on this book is very well structured. A lot of the questions that I was like, how is this actually going to work when struggling through the last chapter's like hands-on terminal time section are all answered here, and they're answered very well. And in fact, all the questions that I had as I was reading this chapter were immediately answered as I kept reading. So that's actually super awesome. And I just want to give a kudos to whoever wrote this and did the layout for it, because I thought it was awesome. The first thing it actually talks about, and the first thing that we therefore will talk about, is the stack and the heap, and actually how they're different. And I have a little bit of context from my university days as to what the stack and the heap are, but they're not something that's going to be super obvious to somebody who's been working in a higher level language for the majority of their career or haven't had experience with lower level systems programming languages. And so this example that they gave about waiters and stuff, I didn't really like. I think trying to make abstractions for the stack and the heap actually just makes life harder to understand. So I'm going to dive in a little bit, but hopefully only a little bit and not a lot of it, because we want to write Rust. We don't want to learn about computers that much. I lied. We want to learn a lot about computers. So this is a Linux programming interface. It's also released by No Starch Press, and I got this copy a long time ago thinking I would need it. Sometimes it's very useful to reference. If I read a chapter in this, my brain feels like it's going to burst. So I'm only going to try to give as much information from this as I think is necessary. It talks about the process memory layout, which is essentially when a process is executed, the structure of the memory inside the computer. So all the ones and zeros addressable in fungible units of 8 bits. We have text, data, heaps, and stacks. And the text and the data are read-only. So the text is the actual instructions of the program, and the data are static variables used by the program. This is important because later in the Rust chapter, it ends up talking about static variables as literals. So the string literal here, in this example highlighted as hello, is going to be written into the read-only part of our program in the data section. And then we have a heap and a stack, which I'll just read out loud here. The heap is an area from which programs can dynamically allocate extra memory, and the stack is a piece of memory that grows and shrinks as functions are called in return, and that is used to allocate storage for local variables and function call linkage information. That sounds like a lot, and it's kind of hard to get unless you've actually seen it or somebody's drawn it out for you, and I'm not really capable of doing that because in my head it's different than how everybody else imagines it. But you can imagine the stack as a bunch of things stacked on top of each other, and I only have 2 hands, so it's not a great example. But I have my stack of hands. The last thing that I put onto the stack is the first thing that comes off of the stack. And therefore, the first thing that was on the stack is the last thing to come off the stack. I can't pull something out from below it. And that's useful to know because it tells us that the stack cannot be fragmented, whereas the heap is like everything laid out on a table and you just pick the piece up from it that you need when you need it. And that's useful for us to know because the heap is kind of accessible but not directly. It needs to have a process of going and getting the thing, which are pointers, and that's slower because we're not just reading the value from memory, we're going to a place where we have more flexibility in how things are stored to actually read them. And so the stack is linear, it's faster, and it's based upon the function that we're executing. Because the stack contains function call linkage information, we know that as we're executing a function, we have some variables inside of that are being used. And when we either call another function, boop, we have a new stack and we'll use that, or we return that we're going to be taking something and putting it back in our stack. My hand motions are terrible. Basically, all you need to know for now is that the stack is linear, the heap is hierarchical, the stack is local, the heap is global, The stack contains variables that cannot be resized. The heap variables can be resized. And the stack, all the allocation and deallocation is managed for you as part of calling a function. And the heap, the explicit allocation and deallocation of variables and memory is necessary. That's probably either not enough information or way too much information, but it ends up talking immediately after about strings, because strings are kind of one of these special things that can fall into both the stack because they have the literal ones that are written to the data segment, or we have things that are stored on the heap, which are the capital S string types. And it talks about this string type and then in fact talks about other string types later. So I put a little sticky note kind of talking through that. The strings that have quotes in them that exist inside the code like this are strings that are in the data type and are literal strings. But when we talk about a capital S string, we're talking about a type, and that type exists on the heap. That particular string can come from a literal, but now exists on the heap, and when we reference a slice of the string like this, we're referencing that heap value. And hey, wouldn't you know it, there's like a little chart that specifically talks about that and how we have a reference to a string slice with the little ampersand and why that's useful for us to know. Which is nice because if you imagine this middle guy being changed in some way, this string slice will be mad, and that's something that's checked for us in the compiler. Going back to the idea of like pointers, whenever we have this pointer to something in the heap, we can consider that parallel to what we'd experience in another language. And I wrote this little check kinda here is mainly because that's the way I've seen it work in other languages, and I didn't see a chart on the next page a little later. But this particular chart here is referencing what normally happens when you have two variables that have the same pointer. You're referencing the same piece in the heap, and if this changes in any way, then we have a problem because it's all predicated upon which one of these guys did that change relative to the other. And you can't do things asynchronously because they're both predicated on the same data, and that's called a race condition, and we don't want that to happen. When you have code like this, where we say, here's a string, and I want to make a variable that references that string somewhere else, we normally copy that data or clone that data to a different place on the heap. And so now whenever one of these makes a change to whatever's there, it's perfectly valid. There's no sort of associated pain with that, which we don't get for free in Rust. If we want the same functionality as other languages, we have to call clone on that particular variable. But in Rust, what we get by default is something similar to C, except we're checking who owns the variable. So if we have this code up here, we say S1 is now some sort of heap allocated string, and we have this guy that's pointing to the heap, and then we say S2 equals S1. S2 now exists, but S1 no longer owns that reference to the heap, meaning that when we try to print down here S1, the compiler goes, yo dog, you're trying to call S1. You don't own it. You're done. Do not go to jail. Do not pass go. Do not collect 200. They call that paradigm moving because it makes sense. You're moving this data. You didn't clone this data. But if we want that functionality, we can just simply call clone, and now we have two different spots on the heap that contain the same information, and we can have both of them work as expected. But shitty, I hear you say. How come I can do that with numbers, but I can't do it with strings? It's because that they're stored on the stack, and the reason that they're able to be stored on the stack is because they're of a specific size that the compiler can know of at the time it's actually creating the binary. And we call these ones scalar values. If you remember from the previous episode, I don't really know what the word scalar means. Scalar values are not able to be reduced anymore. And so since they are of a known size and they're relatively small, we just put them on the stack. So when I say, hey, I want y to equal x, it just says, okay, well, here's this value 5. I'm just going to write it in this new spot on the stack for this value y. Ta-da. The actual technical way we know whether or not something is going to be following this paradigm or this paradigm is based upon whether or not the type has a copy trait. And if it has a copy trait, it specifically means it does not have a drop trait, which is going to be what's used for things referencing things on the heap, meaning that their memory is managed by the stack. Which makes me beg this question, which I assume we should expect to see the copy trait on the string literal type. Which all goes to say that this idea of managing the memory of things inside of Rust is tied to the scope, and the scope we know is tied to other things like functions. Because a function is a different scope, we know that when we bring something in or call a function with a particular value, that needs to be moved or copied. And because this whole giant example here is so gross and ugly, they introduce something called borrowing, which is why I have my tiny note here. Borrowing allows us to say, hey, I'm temporarily giving you access to this thing. Don't change it. And because we know we're not supposed to be changing it, the compiler can check for it and let us know if we've done something that's aberrant. Borrowing is what we call a reference inside of a function parameter. And when we're trying to reference, let's say, a string from a function inside of another function, and we want to have this string accessible later after this function's called, we can pass a borrow to it, so long as the thing we're doing inside this function does not mutate that value. But what if I want to mutate the value? Well, you can do that too with a mutable reference, which is essentially saying I'm taking this thing, I'm going to pass it in, I'm going to change it, but I'm going to give you the thing back, which means that we now know when this variable is being used. So we can, for example, not contain two mutable calls in the same scope because I don't know which one's going to be executed when, and it could potentially introduce a data collision, a data race, a race condition. But if you wanted to have two mutable references to a thing, you can do so by having a different scope for that mutable reference. Which leads us to talking about the string slices, because string slices are immutable references to a particular string inside the heap, and then we can reference from where and to where that particular reference ends. And those string slices are very useful for us to have as parameters in our function because they can work on both the capital string and the string slice, which is kind of what I meant. And those string literals that we talked about earlier are actually just slices in the stack pointing to the data section of our process. It also makes a point to say that we can't combine mutable and immutable references at any point. It's just going to result in an error, which makes sense if we're talking about a data race because, well, the immutable reference might hit after the mutable reference takes place, and then it's referring to something it shouldn't be and have unforeseen consequences. But it makes me wonder if I can have immutable and mutable references in different scopes. Perhaps it's in the book, but I didn't see it. I only saw "The Great Oz has spoken, you are not allowed to have these together." I had these in previous videos, but these little asterisk star things are supposed to be for like things maybe outside of this particular narrative of the book and or the things I'm doing in the code that I wanted to bring attention to. And this first one is saying that we know string literals exist directly in the binary. And if you're using Linux, you can actually find them by using the program strings on a particular binary. And we can use this to see that particular string exists in the hard-coded binary produced from the source code, which is pretty cool. We also learn in this chapter that we can return a tuple if we want to return two different pieces of data from a single function. We also got an answer to the question from last episode about whether or not we can change a vector while we're enumerating through it. It's not possible specifically because the borrow checker will not allow us to get a reference to an enumerated value of that vector and change it. So now let's go to the computer so we can get some answers to the questions that I wrote out as I was reading through this, but also to do some examples that are provided to us in the book as worthwhile examples. I made sure to highlight those in blue. I didn't say that until now because, well, you're going to see them as we're going through this computer part. Wow, hello. For you, it was instant, but for me, it's tomorrow. I needed more time to go through the examples in the book and to understand them. So let's go over those things. Firstly, strings. I have this literal string, and I want to know if it exists in the binary. So let me compile it. It's mad for a bunch of reasons. Don't worry about those warnings. I can run the command strings on any particular binary. In this case, I want to go to target, debug, chapter 4, boom. And I get all of these guys out here that appear to be some sort of ASCII-like code. and I can search for it. So I want to look for, does the string exist in the binary? Hey, look, does the string exist in the binary? Can I print you exist inside of the ones and zeros that is inside this compiled binary? How cool is that? Now we know we can search for these literal strings, and why we know they're in the data partition of this particular program. For our second example, we're following the book's instructions and using this example of takes ownership and makes copy, which makes a difference based upon what the data type is that is coming in as a parameter. So in this takes ownership, we're actually taking some string and we're printing it, but we're not returning anything. If you recall, this is a statement and not an expression. And so we should expect that this print line will fail because this particular S was taken when we provided it as a parameter to this function. Boom. All right, value borrowed here after move. So we could potentially fix this by borrowing it inside of this takes ownership and returning it after. Ta-da! So now we know if we borrow this, we can borrow it in the parameter declaration and it'll be returned afterwards. And so long as we're not mutating this, we're good to go. This was something that I guess is obvious in the book, but the borrowing in parameters is tied to the function declaration, and that ensures that when I as a programmer am going to be using, for example, takes ownership, I know that it's going to be taking a reference to that particular value. And I can't, for example, in this takes ownership, change this from a reference to a string and say, oh, well, this is fine because I'm just giving it a reference to this thing. It doesn't matter if it's going to give it back or not, because this function could potentially do some stuff to string that we don't know. I also didn't run this when I changed it from a reference, but you'll see expected struct string found a reference to string. Consider removing the borrow on S. For our third trick, we have a question of whether or not we can modify things we're borrowing. And so I have the string based from the string literal hello, and I am saying we would want to pass a string slice, a reference of that string, into this change function, which is expecting said reference, and we're attempting to modify it. We know that this will break because this reference here isn't mutable, and calling push string on some string, even if it's just a reference to it, will say, hey, this requires mutability, I don't have a mutable reference, £. Hey, look, it says that some string is a reference and the data it referred to is mutable. That won't work. We can fix this in our fourth example here by creating a mutable string and passing a mutable reference inside of our function, which is defined with a mutable reference with the exact same code. And as you can see here, it's happy. On to our fifth example, I had a question about whether or not we can have two mutable references. And I create a mutable string, I reference it as a mutable reference as S1, and then I print it. I assert this will work just fine. But if we were to have another mutable reference and attempt to call it, we'll have issues if we require the first one to exist. Here we can see we can't borrow S as mutable more than once at a time. We can fix this by having S1 be in a different scope, doing all the things we need to do with it, and then having a different mutable reference in a different scope, which means that we can't ever really have S1 and S2 print at the same time. But we know that this is now memory safe. Not that it's a big difference between this and shadowing, but maybe that example will stick with you. I don't know. For our sixth code example question thing is whether or not we can have a mutable and immutable reference in different scopes. We know that if we have S1 as a mutable reference and S2 as a immutable reference, then we can't actually run them. It'll say, hey, you have a mutable borrow and an immutable borrow, and a mutable and mutable borrows are not allowed to exist in the same scope. That's not cool. So the question is, if we are to split this up into a different scope, we can actually see here that we can't have a mutable and immutable reference at the same time, even if they're in different scopes. So I guess what that means is if we want to do something like that, we have to wholly compartmentalize them. We have to make sure that our references are done before we actually try to create a new reference. Since I already talked about how function parameters that involve references are strictly defined, I want to spend a lot of time on 7. And if you were smart and you were paying attention, you'd notice that there was a jump cut and this code has changed in between the last question now. And it's because I had to do a lot of digging around and asking a lot of questions, and I had some people who were able to help me. So I want to make sure to go through this with as much detail as possible because there was a lot of really interesting things in this. Firstly, this all started because I was in this chapter and it has this section here. Rust has a special annotation called the copy trait, which we can place on types like integers that are stored on the stack. If a type implements the copy trait, an older variable is still usable after assignment. Rust won't let us annotate a type with the copy trait if the type or any of its parts implement the drop trait. So when I read that, my thought was, wow, so I know that things should have a copy or they should have a drop as a binary. It turns out that there's way more nuance to this. The first thing that I started doing was looking at the string type to find drop. It would make sense that it needs to have a drop to drop the reference and deallocate that memory. And there's no drop trait on string. So what's going on? I started digging further and I was informed that the primitive type reference is a thing. So when you make a reference to something, the reference itself is the type. Which is pretty mind-boggling to me. I'm not sure if I would have understood that. There was a tiny snippet inside the book that talked about that. But whenever you have a reference, this type is a reference. And this type actually implements copy. This makes sense to me since now we're talking about references to the string. But if I'm talking about the string object itself that exists in the hash, we still don't have a drop. So I started looking in, and I was informed that there is a drop section in the documentation underneath the operations, and it tells me about what the destructors do inside of Rust. And we can see that destructors consist of two components: a call to drop for a value if this special drop trait is implemented for this type, meaning it doesn't have to be implemented, and that there's this automatically generated drop glue which will recursively call the destructors of all field types of this value. So we know that we don't have to implement drop on any particular type. It says, as Rust automatically calls the destructors of all contained fields, you don't have to implement drop in most cases. And it would appear that the string is that case. Which brings us back to this code sample here. I didn't write this. I had somebody who was kind enough to provide information about how this would actually be called. But we're actually dealing with generics here, and we're going to learn about them later. Basically, I'm just defining a function C that can take a more nebulous type inside of it called T. And normally you'd see T inside the parameters here, but it wasn't necessary for this particular code example. And this colon drop says that we need to have the drop trait available on whatever this T is we provide into this function C. That sounds kind of confusing. I'm sure it'll make way more sense as we dig further into the book. But this will tell us at compile time if string, which is the thing we're providing into C, actually has a drop. Executing this code, we get a compile error because it says the trait bound string drop is not satisfied. The trait drop is not implemented for string. So now we know definitively that things that are on the heap don't necessarily need to have drop. It turns out that this question of, hey, does this drop need to exist for this particular type is sometimes complex enough that the Rust makers decided to add this function needs drop, which will tell you at compilation time whether or not a particular type has non-trivial drop logic and therefore needs more thought given to how it's dropped from memory. And in the circumstance where we're not actually defining how things should be dropped from memory, we're relying on Rust to use its automatically generated drop glue. All that to say is that it's not a binary between whether or not a particular type has copy or has drop. It kind of functionally does, but we don't necessarily expect to see that inside the documentation for any particular type. I definitely did a lot more learning outside of chapter 4 just to get an answer to that particular question, but I want to give special thanks to Kyle, Victoria, Brooks, and Stu in my local Rust chat group that helped me figure out what was going on and helped me understand how to frame that question in a way that made sense. So thank you very much. I truly appreciate it. And for everybody else who's stuck through this entire thing, I appreciate you watching. I recognize that these episodes have gotten a little bit longer than before, and I don't necessarily think that's going to change. The chapters in the book are necessarily going to get more complicated, and I wouldn't expect that the length of these episodes are going to get any shorter. If there's a better way for me to structure these episodes so they're more trimmed down to specific things that I thought were interesting from an episode that maybe wasn't obvious to me at first, then let me know. I'm happy for any sort of comment or critique. And if there was anything inside of this episode or this chapter that was illuminating to you, or you thought I didn't do a good job of explaining or was absolutely incorrect on, let me know in the comments below. I'm super interested in any of your feedback. And thanks again for watching.